So internet and things, those sound like words you understand. They sound like simple words. What I want to do in the next 20 or so minutes is smush them together and show if you put things next to internet in stages, it leads to deeper and deeper implications that will seem to go very far from what you think the meeting is about and likely end right in the middle of where you think it's about. So I want to look at the technology of the Internet of Things in stages. This is a paper I wrote, a number of years ago, 2004, with a student named Danny Cohen. If you don't know Danny, he's at Oracle, then Sun. Before that, he started the Moses chip fab many people use. But before that, at ISI, he was the person who separated what you now know as IP from what you now know as TCP, who said routing a packet is different than controlling the flow of it. And he got interested in an engineering hack we had done. We weren't doing research on the internet and had no idea what this was about. But I was doing device physics of user interfaces and had to connect things. So this was a medicine shelf for the White House for the Millennium. This was furniture at the Museum of Modern Art, stage for the Karamazov brothers. I'm joined by Vicente Gallart from the Institute of Advanced Architecture in Catalonia. This was a house we did with them. It was a performance of a houses theater where when you build the house, you also build the intelligence. Each of these, we had things we needed to connect. But what Intel had on offer, or Qualcomm or anybody, cost too much in dollars, pins, power. And so we did a very simple trick, which is we try to saturate the capacity of communication networks. In these cases, we cared not about data rate or speed to a light bulb, but about cost and complexity. And so we abandoned the usual things you worry about, frequency, amplitude, phase, and just used events. So in Morse code doesn't change when you wave flags or flash lights or click a telegraph, but that's unlike how we communicate today because you're trying to make it optimal. Here, we would throw all that away and it's essentially Morse code for the internet. We would just use events. You hit the system, it rattles however it does, lets it settle. It takes about a microsecond for a building. And so if you're talking less than a megabit to a light bulb, you can completely ignore all the things you know about networking. Just an engineering hack, but it lets us make a web server for $1 that you put in things. Danny pulled together a meeting with Bob Kahn and Len Kleinrock, a number of the internet architects, and what came out was this very interesting parallel to what we thought was just a cheap hack. What is the internet? In the beginning, there was ARPANET, SATNet, PRNet. There were a number of packet switch networks. Either they didn't talk at all, or you had to configure state at the boundary. The big idea then was end-to-end, agree on a representation IP that's the same on any network that carries it, and so if you can push out a packet, it can go over any network. That's what internetworking is. That was the idea that gave us the internet. Today, look at RFID, power line, optical. They have nothing to do with each other. RFID, ISO 18000, IR, IRDA. Each of these standards is wholly unrelated to the others. If you want to go from one to the other, they can't talk at all, or there's the state at the boundary. The same situation that led to the internet holds now for devices. And what we were doing in this project is internetworking, not at the protocol layer, but in the physics. Agreeing in a representation that looks the same so all devices can talk to each other. So it's a recursion on the internet. It's internetworking in devices. Now, so each of these is $1 or so in parts, runs the same code. The only difference is the physics, and they all talk to each other. So it means you can make a web server for $1. The cost is we're throwing away about half the performance. Now, in the history of the internet, IP was controversial when it was born because it's not optimal. And there was an argument, but for whatever I do, I need an optimal protocol. But IP is one of these bottlenecks that by passing everything through it, it's not optimal for any one thing, but it's good enough for almost everything, and it gave us the internet. In the same sense, when you care not about throughput, but the cost of complexity, internetworking in the physics is the same story to bring the internet into devices. So if you want to internetwork devices, the lesson is don't saturate channel capacity to a light bulb. Recognize you need the principles of the internet pushed all the way down into the physics. So that led to, we did a test bed with Schneider Electric and Cisco and Sun and companies like that, looking at industrial automation. This is a little bit, I'll leave a link to this, of a Schneider engineer. So audio up from the computer. What you'd hear him explaining is...
All the nodes that are capable of being controlled, or capable of controlling that node will respond with a double flash like you saw. And if I do nothing within a short timeout period, there'll be a subsequent flash to indicate that I can no longer form a pairing. But if I were to try to form a pairing, and Todd, if you want to...
So I'll leave a link to this. What he goes on to show, each of these is $1 in parts. It's a light bulb and switch. It does IP protocols with a V6 web server over the DC power line. And he's building a data structure. He's building a one-to-many and many-one-to-control structure where the information is distributed with the network. The control grows with the number of devices. Then there's a transparent, stateless interface to the rest of the internet. And then you can run the system through all of that. So then one step in, Vicente and colleagues took that test bed and did this beautiful installation for hyperhabitat. This was for the Venice Biennale. And they looked at what would it be like to have all of your furniture connected in this way.
Microservidores de lo que se ha venido a llamar Internet Cero, desarrollados por the Center for Bits and Atoms del MIT y diversas compañías como Schneider, Sun y Cisco, que permiten conectar los objetos directamente entre ellos sin depender de un ordenador central que los controle. Cada objeto, por otro lado, tiene un botón y un slider que nos permitía seleccionar cualquier hipotético edificio en el mundo en esta matriz que hemos planteado.
What he's doing is the slider controls the knowledge radius. When you cook your paella, it can be for yourself, you can tell your refrigerator, you can tell your friends, you can tell the market, you can tell the supply chain of the city. Each physical object has this virtual echo, and you can, by interacting with the object, control the radius of information to the objects. So it's this beautiful installation of, I don't know how many hundreds or thousands of these embedded IP nodes in this very large-scale installation of what is it like to live with furniture where every part of your furniture is on the internet. So one step in, Internet Zero, inner networking in the device physics. Throw away what you know about all the competing niche protocols and interoperate in the physics. This started with industrial automation. The killer app, though, that then emerged is energy, as Paul highlighted. This was a review we did in Science. Buildings use 3/4 roughly of the energy in the US, and about 1/3 is consistently wasted. It's wasted from inefficiency, but in fact, even more so, it's wasted from deficiency, from just pathology. Buildings are basket cases. From test beds we did of taking these Internet Zero type devices and densely putting them in buildings. This was one at MIT where this shows you the air conditioning turning on at 4 in the morning to be ready for people coming at 8, even though it only takes a half hour to cool. And this is the outside air that was colder than the conditioned air, so all they should do is open the window. This is another building where these are the heating and cooling systems, and they're at war for who gets to control the building. So they take turns thrashing to try to be in charge. Just a disaster. And the reason this persists is an old battle is being refought. BitNet lost to the internet because the internet is incrementally extensible. You can add a server to the internet without needing central approval. The same war is being fought in buildings. Smart grid means many things. Often it means a very bad things. Smart grid is often used to mean a central mainframe-like thing controls the remote appliance peripherals, and you need central control to connect the remote appliance. For Internet of Things to apply to energy, buildings need to run like the internet, where you can incrementally add 1 degree of freedom to it. And these problems persist because today in a building, it costs somewhere between hundreds to $1,000 to add a single control point, even though the incremental device cost is $1 because it's the implied system cost to get it into the central control system. The lessons from the internet is it needs to be incrementally extensible, so 1 control degree of freedom equals the incremental cost of the control. So you need to bring the internet into buildings, but that has a deep meaning. You need to bring it into the infrastructure. It doesn't mean central sensors to a central mainframe, which was the battle we did between BitNet and the internet a few decades ago. So I think the driver app for Internet of Things is likely to be energy. Energy is such a pain point. It's such a, nothing competes. The amount of energy being wasted to stupidity so dwarfs anything else you can do. That's likely to be the coming most immediate forcer. Just a technical note, for this to succeed, it then means every light bulb, every sensor is an IP node. That assumes then you need the services of naming and routing and all of the things Internet does. We'll be doomed, though, if you need an IT department for your light bulbs. The economics doesn't work. And so current work, and this is a version called asynchronous packet automata, is how you take the services at higher levels of the Internet, like naming and routing and flow control, and push those into the embedded devices. So when you connect the $1 devices, at the same time you're actually building a router and you're building the infrastructure for naming. And there's very interesting research, and if you're interested, I can tell you more about how you build those sort of systems, not as centralized routers and servers, but as distributed infrastructure. So as you build the building, going all the way back to Vicente's original vision, you build the building, you build a data structure, you build a computer that all scales with the infrastructure because it is the infrastructure. So that's the first push into Internet meets things. Second push is, we'll be doomed if you have to worry, is your building 16 or 32-bit? And is it a Mac or a PC building? If we're going to fill the building with all the software, how do you write it? How do you describe it? How do you given the lifetime of a building, you don't want to have to port your building to a new OS. And that's led to, this is a part of a much larger project. A growing group of people, certainly including me, believe Turing and von Neumann got it wrong right from the beginning. When computer science was erected on a foundation where hardware and software were considered distinct, and so software can live in a world free of the limitations of physics. And there are a number of scaling issues. A very different route is to write software so it looks like physics. So in this project on logic automata, this is a computer program. A computer program isn't lines of code. A computer program is a spatial structure. And it has all the structure you think of a computer program, of hierarchy and modularity and all of that. But it works, when you zoom a map from Earth down to this building, you change representation, but it's always the map underneath. In the same sense, the computer is physics, it's geometry, and you can zoom in and out and program it, but it's a spatial structure. And so what that means is all of these systems run the very same program. The program now is not lines of code in a processor. The program is a spatial structure that can be run by any of these different systems that can run this kind of code. And so it means when you build the building, you don't pick a processor and write lines of code for it. You actually overlay a program as a spatial structure on a building as a spatial structure. Today, when you buy a computer, you need to pick which processor, which drive, how much cache, which interconnect, all that stuff. The computers we make look like this. They're just homogeneous substrates. And what we're heading towards is you're going to buy them like this. You pick the pounds or the square feet of computing to meet the need of your problem, integrate it in the infrastructure, and if it's not enough, you put on another code of computer, very literally. So this is the second step in. If we're going to fill every degree of freedom in a building with internet-connected computing, which there's compelling applications for starting with energy, we can't maintain incompatibility in that code. You really need to revisit some very basic assumptions about what software is and make software that's a spatial structure for systems that are spatial structures. We're programming a building, and the software needs to be written in a way that reflects you're programming the building. Let's see, that's not me. My phone's there. Somebody's phone is near. So second step in. First step in was Internet 0, inter-networking in devices. Second is, for Internet of Things, you need to start to revisit how you write programs and make them spatial structures. Third step in is, when a program becomes a spatial structure, to load it, you have to grow it. You have to grow a program in a spatial structure. This is showing how we load programs in these homogeneous computers. In turn, that description can describe other things. So this is a CAD workflow that turns geometry into essentially protein folding. So you can start with a shape, turn it into a code, and have the code turn into that geometry. And this is part of a project where we've implemented what I just showed you in DNA and nanoclusters and microfluidics and micromachines. Here's a segment of a macroscopic robot that works like a mechanical protein. It can turn into any shape, up to people-sized versions. And what that leads to is communication was analog. It got worse with distance. Claude Shannon wrote the best master's thesis ever, I think, at MIT, showing if you digitize, you can communicate perfectly. Interestingly, he went to Bell Labs. They spent 10 years fighting over analog versus digital phones. The battle was won, I was told, because the analog managers died. The digital managers took over. We have the internet. Vannevar Bush made the last great analog computer at MIT. Room of gears and pulleys. The longer you ran it, the worse the answer was. Computers are digital. Manufacturing is analog. In the 50s, MIT connected the first computer to a machine tool, but there's no information in the materials. In Paul's state-of-the-art fab, the basic process still is you spread stuff around and bake it. The information is not in the materials. The research I just showed you is we're learning how to have computers not just describe things, not just interface with things, but become things. The program doesn't describe the object, it is the object. We actually compute with materials. We code construction. So bits become things and things become bits. And so we're just at the edge. We had these digital revolutions. They're over. We won. There's a new one coming where we learn to take the programmability of the world in computers and connect it to the world out of computers. It leads to this very interesting parallel. If you go from mainframes to mini computers to hobbyist computers to PCs, the roadmap I just described goes from the mainframes of digital fab to the Star Trek replicator. And the equivalent then to the mini computer is community labs, I'll describe, that have grown around the world. The equivalent to the hobbyist computer is rapid prototyping machines, machines that make machines. And in this roadmap, we're about exactly here. Now, this is one of my favorite pictures. This is Ken Thompson and Dennis Ritchie inventing Unix on a PDP at Bell Labs. That's the moment when computing got down to the scale of work groups, so you didn't have to ask permission to invent something new with it. And email, the internet, everything we do today happens. And so this vision of digitizing fabrication, it's 20 years to the iPhone of digital fab, the replicator in your pocket, but you don't need to wait 20 years to invent the business models and applications of data turning to things and things to data. I encountered that because we set up one of these field labs for NSF, and they spread virally around the world, doubling every year. To give you some examples, Vicenti's Fab Lab at the Institute for Advanced Architecture in Catalonia, they just did an amazing thing recently where they used the rapid prototyping tools to make a complete solar house. So starting with data, making parts on demand, and then this was in the European Solar Decathlon in Madrid, where they got last place in the formal judging, first place in the People's Choice Award. And one of the reasons they got last place is this house was so popular, it had so many people in it, it was bad for the energy use. But this is rapid prototyping on the scale of a solar house. This was an amazing project. We had one of these fab labs in Afghanistan. Telecom infrastructure was a disaster. I'll start this briefly to describe it.
A story about MIT students who helped build a wireless network in Jalalabad, Afghanistan, out of junk. They call it Fab-Fi. That's a mix of Wi-Fi and Fab Lab. Students at MIT's Center for Bits and Atoms have created fabrication laboratories, or Fab Labs, across the globe. Fab Labs are like community centers with machinery and computers that the public can use to create things. The goal is for the community to use and develop technology that addresses their specific needs. And here to talk with us about the Fab-Fi project in Afghanistan is MIT graduate student Amy Sun. Welcome to the program.
Thanks, Robert.
So it goes on to explain using the digital fab tools, making high gain antennas, radios, and now going from community to metropolitan scale. This is a satellite photo wiring up a city with bottom-up telecom infrastructure. And this is a related project using the digital fab tools for a few dollars in parts to make a thin client internet terminal that synthesizes video and microcode, talks to a keyboard, implements internet protocols. And so rather than technical heroes making a $100 computer you ship to the world to solve the world's problems, once you have these digital fab tools, you can make computing on site, on demand, so the skills and jobs are local, and they don't need to all be the same. You can have different ones for big ones and small ones in different languages, and you can start to think of something on the scale of a metropolitan area data network as a bottom-up community project, not as a top-down one. So as this network has grown, we're spinning off nonprofit foundations for invention as aid. Spain's government is doing a very interesting program, bringing target aid countries for training in the fab labs here and then leaving with labs back to their countries. Accrediting a degree program to use planet Earth as the campus, not a location. I did a keynote for EduCause on that about a month ago, and had a great discussion about accreditation at this network campus. Picking up on Paul's last comment, they said, "This is great, we love it. Where are you located?" And I said, "Yes." And by law, you're not allowed to do that. Accreditation is to a place, not a network, and the laws. So they encouraged us to invent a degree, pretend it exists, and let the laws catch up. Then for business models, this is Manchester during the last industrial revolution. They had 3/4 of the world's mills, and now they have 2 football teams. It's been kind of downhill since. We're working with a group of UK manufacturing executives on fab labs there, but with a very interesting vision. This is the lively Manchester Fab Lab. So data comes into this place, it becomes objects. Objects come in, they leave as data. You can view this simply as a place to prototype products, but there's a deeper story. If you look at the history of HP with laser printing and inkjet printing, the inkjet people said, what if you could print beautifully, cheaply, but slowly? Management said, bah, it'll never scale. They had to leave California and hide in Oregon. They went to Corvallis, and they made all the money that let HP win. In the same sense, you can view this as a prototype, but then you go off and do mass production. That only makes sense if you're going to always make the same thing. On the other hand, a world full of these facilities does high-rate manufacturing with a lot of low-rate production. So a world full of lots of low-rate places equals to a high-rate place, but now they can all be different. They don't have to be the same. And so this leads to a industrial revolution 2.0, where everything is produced on-site, on demand, and the prototype is the product. And there's a very interesting story emerging around that. And so I'll end here with the ultimate implication of Internet of Things isn't just Internet to things, but the Internet carries things. Once you have this technology, objects can become data, data goes through the network, and it comes back to objects, and we seamlessly merge them. So in that quick tour, first step in is if you want to bring the Internet into infrastructure, you need to take internetworking seriously. And don't try to saturate bandwidth to a light bulb, but communicate in the way a light bulb works, which is by internetworking and physics. Second step in is if we're going to fill the world with code, we can't be saddled with these legacy assumptions in software. You need to make code look like the physical world to run in the physical world. And then the third step in is once we integrate this finally, it means we're not just connecting to things, but the internet actually becomes a carrier of things, which raises entirely new business models where businesses become networks. It raises entirely new educational models where instead of distance learning from a screen, you can download the campus by getting descriptions and building the instrumentation locally. It really upends a lot of the organization boundaries we live with. Thank you.